Welcome to the Padhai Kar Lo JEE preparation channel. You can practice more problems on this exact topic on our Padhai Kar Lo Android app, link in the description below, or on our website padhaikarlo.com. Today's topic is calculating spectral line wavelengths in the hydrogen atoms Balmer and Brackett series, a direct, formula-driven application of Bohr's model. Let's begin. When an electron in a hydrogen atom transitions from a higher energy level to a lower energy level, it emits a photon of a genuinely specific, precisely defined wavelength. And the Rydberg formula calculates this wavelength directly. 1 over lambda equals r, the Rydberg constant, times the quantity, 1 over n1 squared minus 1 over n2 squared, where n1 is the lower energy level the electron lands on, and n2 is the higher energy level it started from, with n2 always greater than n1. Different spectral series are named specifically according to which lower level, n1, the electron actually lands on. The Lyman series has n1 equals 1 landing in the ultraviolet region. The Balmer series has n1 equals 2 landing partly in the visible region, and the Passion, Brackett, and Fun series have n1 equals 3, 4, and 5 respectively, all landing in the infrared region. Within any single given series, the specific transition from the very next higher level produces the longest wavelength line, while transitioning from n to approaching infinity produces that series' own shortest possible wavelength, called the series limit. For the Balmer series, n1 equals 2 and the first line, called h alpha, comes from the transition n2 equals 3, dropping to n1 equals 2, substituting into the Rydberg formula, 1 over lambda equals r times 1 over 4 minus 1 over 9, which simplifies to r times 5 over 36, using r approximately equal to 1.097 times 10 to the 7 per meter. This gives a wavelength of approximately 656 nanometers, which correctly, genuinely falls within the visible red region of the spectrum HALTY. Why the Balmer series is the only hydrogen spectral series with lines actually visible to the naked human eye. The Balmer series limit, as n2 approaches infinity, 1 over n2 squared approaches 0, giving 1 over lambda equals r over 4, which works out to approximately 365 nanometers, at the boundary between visible violet light and the ultraviolet region. The Brackett series has n1 equals 4, and lands in the infrared region. Its first line, from n2 equals 5 dropping to n1 equals 4, gives 1 over lambda equals r times 1 over 16 minus 1 over 25, which simplifies to r times 9 over 400, working out to a wavelength of approximately 4050 nanometers, well within the infrared region, genuinely consistent with low energy transitions, landing on higher, more closely spaced energy levels, producing correspondingly lower energy, longer wavelength emitted photons. For any G numerical in this specific topic, first correctly identify n1 from the named series. Lyman equals 1, Balmer equals 2, Passion equals 3, Brackett equals 4, Fun equals 5. Then correctly identify n2 from the specific line described. First line means n2 equals n1 plus 1, second line means n2 equals n1 plus 2, and series limit means n2 approaches infinity. Then substitute directly into the Rydberg formula and solve. A frequently tested trap. Remember, energy and wavelength are inversely related, so the series landing on the lowest level, Lyman, has the highest energy, shortest wavelength photons, while the series landing on the highest level has the lowest energy, longest wavelength photons. Let's recap. The Rydberg formula, 1 over lambda equals r times 1 over n1 squared minus 1 over n2 squared, calculates hydrogen spectral line wavelengths directly, with each series named by its own landing level n1. The Balmer series n1 equals 2 is the only series visible to the naked eye, with its A-alpha line at approximately 656 nanometers. The Brackett series n1 equals 4, lands in the infrared, and for any numerical, correctly identifying n1 from the series name and n2 from the described line is the essential first step. That's spectral line wavelengths in the Balmer and Brackett series. Keep the series to n1 mapping and the Rydberg formula sharp. They cover almost every hydrogen spectrum. Numerical JEE asks. If this video helped, please like it and subscribe to Padhai Kar Lo for more JEE preparation content just like this. See you in the next one.